All right, so first set of notes for Unit 2. This is Thermo Part 1. Okay, Thermo Part 1 will be in notes 1 and 2 for this unit, and then the third set of notes will be on gas laws, which will be very much a review of last year's stuff because gas laws, doesn't have a whole lot of new information. We will be going into a lot more depth with the thermo than what you saw last year or the year before in your Chem 1 class. Okay, so be at a more conceptual level too, deeper understanding. So really pay attention to the explanation parts, okay, and looking and trying to figure out how to explain the chemical concepts in words. So I can explain the exchanges of energy for different systems, and particularly we're going to be looking at solutions and reactions for this particular grouping of thermo. Identify change in energy for a system as being endo or exothermic. Define change in enthalpy of a reaction, the basic term here. Calculate the heat absorbed or released in a reaction using molar enthalpy. Which is basically stoichiometry with the enthalpy added in. Calculate the enthalpy of reaction using Hess's law. Okay, so that's a whole new technique, although Hess's law problems I quite enjoy because they're like working out a puzzle, so they're kind of fun actually. So let's start off with defining energy. The ability to do work or transfer heat. Okay, work is the energy used to cause an object that has a mass to move. That's what we're talking about when we're talking about work energy. There is a formula, work is equal to the force times the distance. Now this is more going to be found in physics. We're not going to be looking at the work aspect so much because the work aspect of chemical reactions ends up being eventually derived out of the equation and canceled out of the equation. So when you're looking at work, yes, we're going to talk about it briefly because it is part of the internal energy of the system. It eventually gets canceled out, and all we're going to care about is the heat in terms of chemistry. That's the important part. So that's down here. The energy used to cause the temperature of an object to rise is called heat. So we're really going to be focusing more on that aspect of what's going on with the energy exchange. Okay? Any questions on that? Alrighty, so let's talk some kinetic and potential energy and maybe reframe our prior knowledge of what they are into the new definitions. Anybody have an idea of kinetic energy? What would you say that is? Anyone? Yes. Moving energy, energy of motion. I can agree with that one. That's pretty good. Alright, before we get there, let's also hit on the law of conservation of energy. Energy can be converted from one form to another, but it's neither created nor destroyed. Okay, total energy content of the universe is constant. So this is important, like before we get into the kinetic and potential, knowing that it changes form. It can go mechanical to thermo, to chemical, electrical. There's so many different types of energy out there, but it does not disappear. And it's not created, it just transforms. And that's all we're saying there. We'll go back over this again because it is the first law of thermodynamics, so we will hit it again later. Capacity to do work or produce heat, that falls under that energy category. Now, back to kinetic. No, potential. Now kinetic, there we go. Kinetic energy is the bottom definition. Energy due to motion of the object, and it depends on the mass and its velocity. So this is a new equation. This one's found on your formula sheet. We'll be using it more with the gas laws and looking at that. Potential energy, energy due to position or composition. We're going to expand on our idea of what potential energy is. Because what do you think of when you think of potential energy usually? Ball rolling down a hill. I've heard that analogy multiple times. Yes. Okay. You're at the top of the roller coaster, you have a ton of potential energy, right, before you start going down. That's very good positional energy, and that's also falls kind of under the mechanical aspect, and that's more physics than what we're going to be talking about. What we're going to be talking about more in terms of potential energy is the energy stored in the bonds of the chemicals, because that energy, can be unleashed and a lot of different energy change, okay? We'll be talking about that in terms of our potential energy. So speaking of the equation that's on your sheet, this one is the 1/2 the mass times the velocity squared equals the energy. Like I said, we'll be using this more in the gas law part of the unit. But yes, mass is a factor and the velocity is a factor in determining the kinetic energy of the particles involved. Okay, so you'll be looking at the mass and the velocity to determine that. And it is virtue of its motion, okay? And this diagram showing the girl at the top of the hill giving her high potential energy. She's not moving, so she has 0 kinetic energy. As she's going down the hill, her potential energy is decreasing and the kinetic energy is increasing because she's speeding up. Motion, has more motion. Now, this is what most people think of when they're thinking of potential energy. Initial position of the ball. If it's higher, it's held in place. The top of the roller coaster kind of idea, that it has a lot of potential energy. In this case, the ball A would have higher potential energy than ball B. But if we see here that ball A had been dropped and it displaced ball B here, then ball B now has more potential energy because it's higher up than ball A. This is more of the mechanical definition falling under the physics realm. We're going to be looking at it more from this aspect. We're going to be looking at this one, okay? The net electrical charge, chemical bonds, internal stresses on systems, pressure changes and manipulation of things on chemical reactions, okay? Equilibrium systems. Those are going to be our looking at the energy changes going on. Net electrical charges and just flow of electrons, that's going to be in electrochemistry. So we'll see some electrical energy changes there. That'll be in Unit 6 a little bit later on. But we'll be looking at the chemical energy stored in the bonds. That's the huge part of the potential energy that's going to take place here, where we're going to be looking at it in terms of potential energy. That energy stored in the bonds of the chemicals, you know, you break those bonds, you release energy, you reform bonds, you know, that takes some energy too. So there's this net overall measure of what's going to take place in a chemical reaction like that, where you're forming new substances. Any questions on kinetic or potential energy? And looking at it from the chemistry standpoint. All right, units of energy. Mainly going to be working with the joule or kilojoules. Sometimes you will see calories out there, okay? Don't forget 1 calorie equals 4.184 joules. That's also the same as the specific heat of water. 1 calorie per gram degree Celsius, 4.184 joules per gram degree Celsius. That is the measure of specific heat for water. Okay. The joule actually is a derived unit. It's kilograms times a meter squared over second squared. I don't know if you've ever looked at it that way, but it is, you know, a derived unit. And we'll be talking a lot in kilojoules and joules throughout the year. That will be the main reference point of our energy unit. Okay? Any questions on that? So, calorie versus joule, but we'll see kilojoules and joules more often. But you can also use kilocalorie. You can add that one on to as a prefix. That's the more common one because the big C calories that you find on your food labels, that's actually a kilocalorie, which is 1,000 of the small C calories. I don't know if you ever do that, but really, yes. So when you're looking at it, it says 150 calories on that Coke bottle or whatever you're drinking. It's really, you know, 150 kilocalories. Okay. All right. Definition: system versus surroundings. The system includes the molecules you want to study. So these are the chemical species are always going to be considered the system. Chemical species involved. The surroundings are going to be everything else. So if I'm looking at this particular example, you have this vessel, this piston here, and inside the piston we have hydrogen hydrogen and oxygen. If I'm looking at this piston too, the white little circles are smaller than the red little circles, so I'm going to deduce that the red ones are oxygen because they're a little bit bigger than hydrogen. Okay. Also, the piston itself is part of the surroundings. The cylinder, okay, part of the surroundings. I'm assuming that the only things inside the piston are the hydrogen and oxygen. If there was air in there, then that would also be part of the surroundings, okay? But I'm assuming it's just those chemical species inside the piston. So that would be the system. Everything else around it would be the surroundings. Does that make sense? Alrighty. Now, heat. Heat flow. You gotta start thinking about the way heat works. Heat always goes from the warmer object to the colder object. So when I put my hand on the board and my hand feels cold now, that means that the heat is transferring from my hand, which is warmer than the board, into the board, which is not as warm as my hand. So heat transfer is always from the warmer to the colder object. Any questions on that? Okay. Now on to this thermodynamics. Well, first law of thermodynamics we know is the law of conservation of energy. And we study the energy and its interconversions, and that would be under the whole umbrella of thermodynamics. Like I said, we're focusing on the delta H part of thermo right now, and when we get to unit 6, we'll be adding in the entropy piece and the Gibbs free energy piece that also goes with thermodynamics. Okay, so law of conservation of energy gives us that first law of thermodynamics. All right. So energy is not created or destroyed. That is the first law. So what do you need to write down? What is important? This is probably what you need to write down. Universe. Total energy of the universe is constant. If you haven't already written that down. And then this part. If the system loses energy, it must be gained by the surroundings. And it is of equal magnitude. Okay? This graph here looks very complicated, although it's really not. This is the initial state of the system, okay? So if the system, okay, is losing loss of energy from the system, represented by the blue arrow downward, okay, to its final state here, the system lost energy, okay? Then that means over here from this one, showing you that the gain of energy by the system represented by the arrows pointing upward to its final state. Energy is gained from the surroundings, okay? But it is of equal magnitude, okay? So if you're losing or gaining, it's going to be, so if this was losing right here, that means the surroundings gaining that amount of energy. This one was gaining, the system was gaining, that means the surroundings are losing that same amount of energy, or it's being absorbed from the surroundings is another way to say that. Of equal magnitude, it's a transfer. All right, so internal energy, it's one of these state functions, and it has this equation where you have the delta E. Does everybody know what the delta in front means? Change of, right? So you're going to see lots of deltas in the equations on the formula sheets and equations throughout the year. That always means change of. And if we're doing a state function, it's always going to be the difference between the initial and the final states. So the final state minus the initial state is going to give us the change in the state, okay? Now, we're going to discuss fully in detail what a state function is, but there are so many equations in AP chemistry and in chemistry in general that are going to follow this route where we're looking at the initial and the final states. We're not really looking at the pathway in between, how you got from to the end. We're only caring about what did you start with, what did you end with, and what's the difference. Not the pathway. Pathway is a different realm here. Now, basic idea here for internal energy lost to the surroundings, your delta E should be negative. If energy is gained by the system, your delta E would be positive. Now, delta E is not a main focus of this class. We're not going to do too much with it, except for show you how it helps derive our delta H. We need enthalpy. We need to talk about the heat. Where does that delta H get derived from? Well, it's partly from this internal energy equation. And internal energy, what does that mean? So, looking here, if we have hydrogen and oxygen combining to form water, the initial energy is greater than the final, okay? So you're looking here, here's your initial energy state, here's your final energy state. So when those two things combine to form water, where does this energy go? That difference heads to the surroundings. So energy is lost by the system. There's more energy in the bonds of the hydrogen and oxygen than there are in the bonds of the water. So that energy, once it forms the water, has to go somewhere. It leaves and goes to the surroundings. And then it also, when it's lost to the surroundings, we know delta E is negative. That's why it's showing the delta E is less than 0, because it's negative. All right. Once again, not having to memorize this or anything, but I just am showing you this is to show you how delta H gets derived. You don't really have to know the delta E equals the Q plus the W. The Q symbol always represents heat, by the way. The W, of course, is going to mean work. So anytime where you see Q, when we're talking about thermo, it's always referring to heat. So when heat is added to the system or work is done on a system, its internal energy will increase. Adding heat, doing work on the system, both are positive results for that internal energy. The opposite is also true. If heat is lost from the system and work is done by the system, then your delta E is always going to come out negative, and the system loses. But if you have like heat being gained by the system but work being done by the system, they're opposite, then you have to look at the overall net to figure out whether or not overall the energy is being added to or lost from the system. Same thing is true if work is being done on the system but you're losing heat. When you have the opposite variables there, you would look at the net overall to figure out which way the internal energy is going to go. But we, luckily, because it derives out, we get rid of that work variable, so all we have to focus on is the heat, because the work variable gets canceled out for us. All right, one thing to look at here, of course, determining whether the system or surroundings, what we're looking at is endo or exothermic, being able to label it. When heat is absorbed by the system from the surroundings, it's endothermic. And one thing I want to stress here too is the temperature from the thermometer or the temperature probe. When it's measuring, it's always measuring from the surroundings perspective. So if it's endothermic, what do you know about what happens to the temperature? If you put two things together and they're reacting and the temperature decreases, it would be endothermic. You put two things together, the temperature increases. Exothermic. So you always have to remember that that temperature probe or that thermometer is measuring from the surroundings perspective, because you have to be able to get the correct sign out of it. Now, looking here, when heat is released by the system, exothermic, the temperature should go up on the thermometer because it's in the surroundings. Okay? So you should see an increase in temperature for exothermic. And we know that the system is losing there, and you would get a negative delta H versus a positive delta H for endothermic. Any questions on these terms? Because now we're going to start doing some thinking and start talking and trying to figure out the concepts here in the concept check. All right, first concept check. And if you've already talked through this one and explained this one, move on to the next one. Okay, start talking, explaining them. So let's talk about here, is the freezing of water endo or exo? First of all, which one is it, endo or exo? Exo. I think we all came up with somehow that it's exo. Okay? That means the freezing of water is releasing energy. Okay? So in the process of the water solidifying, we have some release of energy. Now, let's think about this. This applies to phase changes. Phase changes are a little bit different than chemical reactions in terms of the way I like to think about it. I have these liquid particles of water, and they're moving around and flipping, and they have a lot of free movement. Okay? So that means when they start to slow down, they're losing what? Kinetic energy. You know, that energy of motion, they're now losing it because they're slowing down. They're establishing those IMFs, those hydrogen bonds, and forming a fixed position, okay, and becoming solidified. They're still vibrating in place. They still have a little bit of kinetic energy, but they've lost a lot of kinetic energy that they had when they were in the liquid form because they had a lot more free flowing. So that kinetic energy is being lost in the forming of the IMFs, those hydrogen bonds, and we end up exothermic here. Now, this is a good way to remember it. Forming is warming. When you are reforming either bonds or IMFs, okay, remember there's a difference between IMFs or bonds. You know, the intermolecular forces are the weaker ones. Okay, the bonds, we're talking covalent, ionic, you know, some of the intramolecular forces, those Coulombic attractions, those also, you know, can be formed, but when you're establishing forming is warming, that always falls under the exothermic category. Okay, the opposite is true then. This is the phrase we like to use. Axing is taxing. So, you know, overcoming IMFs or breaking bonds is going to do what? Require energy. And we know anything that absorbs or requires energy is going to fall under which one? Endo or exo? Endo. Okay, so axing is taxing. I don't know if that's spelled right. I don't know how you spell axing, but maybe there's an E in there. I don't know. But forming is warming. So when you're going the direction of condensing, freezing, or depositing, this is for phase changes. So condensing, freezing, depositing. What's depositing? Anybody remember that? That's gas directly to solid. Yes. Okay, gas directly to solid. Any of those, you are going to be forming IMFs. If you're forming, it's always going to be exothermic. Okay, so if you think about it that way. So that means the other three phase changes are going to be opposite, right? So melting, boiling or vaporizing, and subliming. Those all require energy to overcome the forces, to spread out the particles. These all are going to fall under endothermic, right? These are all going to be endothermic. That's a little bit different for chemical reactions. We'll talk about those in more detail next set of notes, because there's an overall net that has to happen in a chemical reaction. But remember these kind of concepts that will help you with the phase changes definitely. Okay, thinking about the energy. So going with that, let's look at our next example here. My hand, your hand is the system. If gets cold when you touch ice, that's because what? Energy is leaving your hand. So therefore it must be, and we're referring to from the system perspective here. So now the opposite is true. The ice, okay, is getting warmer. Okay, so the ice is absorbing energy. So it should be endo. Good. Now, water boiling. Okay, get it up to boiling. So it's going to go from liquid water to steam or water vapor. What do you think that should be? You gotta give it energy to do that, yes. So let's look at the opposite. Water vapor condensing on a cold pipe. It's releasing, yes, and reestablishing those IMFs. And ice cream melting. Yes, adding in energy to spread out the particles to overcome some of those forces. Now, fun. Each of the following define a system and its surroundings and give the direction of the transfer. So take a look at that. Discuss. Try to think about it in terms of chemical reaction here. Okay. So, for A, which one is the system? Methane. Okay, so when you're lighting a Bunsen burner, yes, you light a match, or you use a striker or something like that to give it a spark. That's the catalyst part that gets it going. But the combustion part, the exploding part, always is going to give off what? Heat. So this one's always going to be exothermic, right? So the transfer is going from the methane to the laboratory. Very good. Okay, so methane's the system, the lab is the surroundings. Heat's going from the methane to the lab room. That's why we feel the heat, because we're sitting there in the surroundings feeling the heat.
Does this mean this is exo?
Yes, that means this is exo, although it wasn't asking for it being exo, it just said the direction of the transfer. So, yes. The methane's actually changing into carbon dioxide and water because it's combining with oxygen in the air. So it's not, but we feel the heat. So when those bonds are breaking in the oxygen and the methane, okay, that is an endothermic process. When they're reforming to form carbon dioxide and water, which are the products, that's forming as warming. That's also an exothermic process. But the amount of energy needed to break the bonds is less than the energy that's being released in the reforming of the products. That's why we feel the heat, because some of those energies in the bonds of the original reactants are giving it, it's coming to us in the surroundings. Combustion is always going to do that. The higher energy reactants, when they break, the energy of the products is always lower, so the net result is some of that energy has to go somewhere and ends up going to the surroundings. We feel the heat.
So all combustion is exothermic.
Always. Mm-hmm. Yes. Now let's look at the second example. Water drops. Sitting on your skin after swimming. The water drops with the system. The skin would be the surroundings. Now, this is the whole process of why we perspire to cool our bodies, if you think about it. Water drops are absorbing the heat from our skin, and when they evaporate off of us, they take that heat away, becoming the gas. So, absorbing it means this process is what? Endothermic. And if you think about it, anytime water's evaporating, that falls under the changing from a liquid to a gas, so it's got to be endothermic as well. All right. Hydrogen gas and oxygen gas react violently to form water. Explain. This one should take you all of 2 minutes, hopefully. Go for it. So yes, the context clues here is the reacting violently. Okay, and you know that one of your reactants happens to be oxygen. That means some sort of explosion, combustion, kaboom, right? So then, if you think about it, which one has to be lower in energy? You have, H2 plus plus O2 giving you H2O. If I balance that, that would be this, right? Thinking about it though, if heat is going to the surroundings because it's combusting, exploding, which one has lower energy stored in their bonds? The water is going to, because some of the higher energy that were in our reactants has now left and went to the surroundings. That's why we feel the heat. So this one's definitely going to be lower in energy in terms of the chemical bonds. Okay? Does that make sense? So then the breaking of the hydrogen-oxygen bonds releases, gives off a lot of energy. It takes energy to break them, of course, a little spark. But then when the water bonds reform, that's not at the same high energy as the original reactants. The energy escapes and goes to the surroundings. We get warm from it because that's combustion. All right, so looking at this, I do not want you to write it all down. Not at all. Okay, what I want you to write down is this top part right here. Okay? Constant pressure, the change in enthalpy is the heat gained or lost by the system. The rest is just showing you the series of equations as to how we get delta H and how it's derived from the internal energy and the work equations. There is a work equation that is used to calculate the pressure and volume, compression and expansion of a gas. Okay? And this is all done at constant pressure, like, pretty much at 1 atmosphere, the atmospheric pressure at sea level. Okay? Those kind of standard conditions. But what you'll see here is that equation, the work one, the internal energy equation. Then we have this delta H equation that combines the internal energy equation with the pressure, volume, work, as focused on, calculating it for the gaseous substance. But when you substitute it in, the work ends up canceling out, so we don't look at the work anymore, and now all we care about is that change in enthalpy equals the heat at constant pressure. So you can go into more depth and look this up if you're really interested in how it's derived, but that's how it's derived. And like I said, we don't really look at the work stuff here. That's all physics. You can have fun in physics. We're going to concentrate on the heat, though. The heat either being gained or lost by the system, and that is our change in enthalpy or our delta H. Does that make sense? Okay, so don't worry about all that equation stuff. This is just showing the setup of how they work, this equation with the pressure changing in volume, how they're measuring the reaction with the gas here. Okay, that would be for that particular equation if you were measuring for pressure or volume and the amount of work done on the piston. That's where that comes from. Not a big deal, not really anything we need to care about. Like I said, we're caring more about the state function of change in enthalpy, which is QP at constant pressure. Our generalized equation is the state function where we're looking at the products, which would be like the final state. This is our final minus our initial. Because remember we talked earlier about the state function. We care about the beginning, we care about the end, we care about the difference, we don't care about how we got there. The pathway is how you get there. State functions only focus on final and initial, not the middle or the path. We will start looking at the middle or the pathways when we talk about kinetics, the speed of the reaction. That's something that we'll engage and talk about the pathway. But most of our other stuff will be just looking at initial, final products, difference. That's what we care about. And that's what falls under that state function definition. So keep in mind, the pathway does not matter. Like for instance, maybe we all needed to meet up at the gym in the school at 4:30 p.m. and you're coming from 3:07. We all will probably take different paths. I might go down the back stairs, some of you might go down the B hallway, go down the stairs to the right, some people would go left and go down the other by the elevator. Everybody's taking different pathways, but meeting up at the gym. So really all we care about, if we started in 307, we ended up at the gym. That's all that matters. Doesn't matter which way you got there. That's what we're talking about. We're talking about state function. Okay? Any questions on that? Alright, so just looking at this particular example here, once again, the products minus the reactants. This is the combustion of methane. You see methane up there plus oxygen gives you carbon dioxide and water. What I just want to point out to you is, yes, we know it's exothermic. We know the combustion is going to give off energy. So over here, it's showing going from the products down here to the reactants. It's releasing all that energy to the environment. What I want to point out to you, although this isn't really a reversible reaction, but there are lots of reversible reactions in chemistry. If we were, say, to go from the carbon dioxide and water to the reactants here, this case it would be opposite. It would be endothermic, but the magnitude, the number of energy, the 890, does not change. The magnitude is still the same. It's just the opposite direction. So this, in this case, we would make it a positive. It would be plus. Okay? So keep in mind that's going to happen. They're going to be opposite sign but same magnitude. All right. One other thing, quantity delta H, when it's called enthalpy of reaction, it also means heat of reaction. So if you see the word heat of reaction, they're referring to the enthalpy of reaction. And sometimes it's written like this, delta H RXN. Lots of little nuances. Okay, so you might see a delta H RXN like that, and it's referring to the enthalpy of reaction or the heat of reaction. They are all used interchangeably. Okay? Once again, here showing you the exothermic process of hydrogen plus oxygen giving you water. And as you can see, it releases a lot of energy based off of our energy diagram. Here is the energy state of the water. Here's the energy state of the reactants. All this energy gets lost to the surroundings. All right, so let's go over the truths here. Enthalpy is extensive property. Does everybody remember what extensive means? It does matter the amount, yes. So intensive is the one where it doesn't matter the amount. That's like density, specific heat, those kind of things. Why are we saying that heat is extensive? Well, just think about this. If I'm going to burn a twig, I'm going to burn a log. Which one's going to produce more heat? The log's going to produce more heat. It has more material, so the obviously is going to burn longer and have more heat. So remember that enthalpy, heat, is going to be extensive here. Delta H, the forward is equal in size but opposite in sign for the delta H of the reverse. Last but not least here, delta H depends on the state of the product and the state of the reaction. We're reactants. We're talking about here now too for phase changes. So liquid versus gas versus solid here. As we said, like the gas particles have a lot of kinetic energy, they're moving freely. Whereas the liquid particles, they have some kinetic energy, are freely moving. Solids are in fixed position, just vibrating. So they definitely have different heats and energy exchanges based on the physical state of the matter, of the products and the reactants as well. So keep that in mind. And we'll look at specific examples that pertain to that as well. Any questions on that? Let's look here at a regular enthalpy stoichiometry problem. Here we have propane burning and oxygen giving us carbon dioxide and water. They gave us the delta H for the reaction. This is like per 1 mole of reaction. Now, every time this reaction is run, 1 mole of propane burns at 5 moles of oxygen, giving us 3 moles of carbon dioxide and 4 moles of water. So every time this reaction run, that's the ratio of all the substances. So per reaction, per 1 mole of reaction, this is what's going to happen here. Now we're starting out with 5 grams of propane, and we want to know how much, if we have excess oxygen, how much energy will be produced by that, okay? So let's start out here. Grams of our propane. This is like a regular T-chart problem. What do I need to do to my grams? Change it to moles, okay? Give you the molar mass real quick, okay? So now here, okay? So 1 mole of propane is going to produce how much heat here? Correct. So for every 1 mole, that's how much energy is for the entire reaction. Then you calculate it, and as you can see, the grams cancel with the grams, the moles cancel with the moles, and we end up with the kilojoules for, you know, this particular amount. What do we get for this? You calculate it. Ends up being, anyone? Somebody's calculating. Yes, negative 252 kilojoules. That's one way to state it. What's another way to state it? 252 kilojoules is released. And how do I say it's being released? Negative delta H tells me it's what? It's exothermic. It's going to the surroundings. So you can either state it this way. That's saying, you know, that the negative means it's leaving the system going to the surroundings. Or you can say it's being released. That also is stating it's going from the system to the surroundings, either or is correct. Okay? Now I want you to try the next one. Try to set it up. So we're starting out here with our 5 grams of oxygen this time, different reactant. Still works the same ways. We change this to moles. Okay, 1 mole of O2. But in our reaction now, every time this reaction runs, you need 5 moles of oxygen. So we have 5 moles O2 for the same amount of heat here, except for I think I put too many 2's in there. Let me correct that. Okay. So every time this reaction runs, you have to use up 5 moles of the oxygen per to reach that negative 2,221 kilojoules, or that amount to be released. So we end up getting what? 69.4 kilojoules. Good. Or you could say 69.4 kilojoules is released. So once again, this is exothermic. It's combustion. Of course it's exothermic. Okay? Yay, we're right. All right. So let's just go through why we're going to use Hess's law so we can start there next time. Hess's law is helpful when we're trying to figure out delta H for a particular reaction, because some of these are very hard to measure in the laboratory. You have to have like perfect bomb calorimeters that are completely insulated, because you can lose heat so easily. So it's a very inconvenient to try to measure heat changes. Once again, you need perfectly insulated labs and lab equipment in order to really get a good reading. However, because these things have been tested by people in those kind of environments with that kind of equipment, there are lots of published lists of delta H values. Now you will find a published list in the back of your textbook in the, reference section. They have tons of the delta H values in there. Now, of course, that you would never be expected to memorize them. They will be provided for you in the problem. But there are tons of delta H values out there. So we can use that information and perform a calculation that Hess's law has proven to be true to figure out the delta H of the overall reaction. So that's really the reason that Hess's law is utilized all the time, because measuring it can be quite a taxing process of really getting accurate measurement. So instead, I'm going to use the published values in order to calculate. There is one more point here. Just going to wait for one more minute. Okay. Why Hess's law? Okay. The thing is, what we can remember about Hess's law is that it doesn't matter. The enthalpy is the same. This is what you need to write down. Enthalpy is going to be the same. It doesn't matter if it takes place in one step, which would be us trying to test it in our lab, or in a series of steps, which is where you would go from the published. This would be the published data. You would look up the series of steps and do the calculation rather than trying to do the one step in the lab and get inaccurate data. Okay? So we're going to use the series of step method of the published data so we can figure out the overall delta H of the reaction. Hess's law problems, like I said, are very much like puzzle type pieces, puzzle problems. They're not too difficult. We will start there next time with Hess's law. So what I suggest you do is work all the problems in the problem set up to the Hess's law problems and skip those for now. Okay? And then you'll be ready to just finish those last couple of problems on Wednesday night or